Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to finish going through Chapter 4.2 and look at RLC circuits. In your guided lecture notes, we're going to be starting on page 15, Modeling Electric Circuits. An electrical circuit is a path or a line through which electrical current flows. The path may be closed, which is joined at both ends, making a loop, or open. A closed circuit makes electrical current flow possible. To describe current flowing through a closed electrical circuit, we can start with some definitions. So first, current is the rate at which electric charge flows past a point in a circuit. If we let I of t be the current and Q of t be the charge, then I of t, your current, is your rate at which the electrical charge is passing through a point. It's a rate, it's a derivative. While voltage is what makes electric charge move. It is the push that causes charge to move in a wire or other electrical conductor. Now, if you're not familiar with electricity, or if you have not taken an electrical engineering class, this will be an introduction to these two ideas of current and voltage. However, I will acknowledge I am not an electrical engineer, so my explanation might be a little bit more hands-on or using familiar language than maybe you'll see in your EE class. So a note to us. It is the current that what can be fatal and kill you, not the voltage. So to some people it may seem that a shock of 10,000 volts would be more deadly than a shock of 100 volts. But this is not so. The real measure of a shock's intensity lies in the amount of current, measured in amperes, that is forced through your body. While any amount of current over 10 milliamps, or 0.01 amps, is capable of producing painful or severe shock, its currents between 100 and 200 milliamps, 0.1 or 0.2 amps, that can be lethal. So this would be your lethal range for electrical shock. Now, for a simple closed electrical circuit, shown below, Kirchhoff's voltage law tells us that the input voltage that's supplied by a source or a battery here must equal the sum of the voltage drops around the circuit. In our circuit, there are three components where we will see voltage drops. There's a resistor, R, an inductor, L, and a capacitor, C. Hence, the circuit is commonly referred to as an RLC circuit. However, in our textbook, our author has referred to this as an LRC circuit. He has just changed the order of the letters. And this is for helping to remember how to write your differential equation that'll model how current is flowing through this circuit. The way you can visualize this is that you introduce some voltage to your circuit. Current starts flowing through your circuit. It goes through the resistor, it goes through the inductor, and it comes to the capacitor. Once it reaches the capacitor, your charge starts to build up on this side of the capacitor. It does not jump to the other side, but what it does is it builds up to a maximum. Think of this like as a water storage container. It builds up to its maximum capacitance, and once it reaches maximum capacitance, it sends your current back the other way through the inductor, through the resistor, passes your voltage source, picks up the current that was lost, comes over to the other side of your capacitor. Again, it starts to build up charge on this side of the capacitor. And once it's reached its capacitance, its maximum charge, the process starts over again. And this is what gives us our view of an alternating current. As it passes through each of the resistor, inductor, or capacitor, this is where Kirchhoff's voltage law says that we're going to see a voltage drop. This is where we're going to lose some of our current. So let's look at this. How do we describe these voltage drops across the resistor, inductor, and capacitor? So the voltage drop across your resistor. The voltage drop across the resistor is proportional to the current. It's proportional to the current passing through the resistor by Ohm's law. This proportionality constant R is the resistance measured in ohms. As an equation, though, your voltage drop across the resistor is proportional to your current, where R is your proportionality constant. Your voltage drop across the inductor. This is according to Faraday's law. Says the voltage drop across your inductor is proportional to the time rate of change of the current passing through it. So it's proportional to your derivative of the current passing through it. The proportionality constant L is called the inductance, and it's measured in henries. As an equation, the voltage drop across your inductor is proportional to the time rate of change of your current. So it's proportional to your derivative of your current. Lastly, there's a voltage drop across your capacitor. The voltage drop across the capacitor is proportional to the charge on the capacitor, where the proportionality constant is written as 1 over C, where C is the capacitance of your capacitor, measured in farads. If you've never seen a capacitor before, then this is a good visualization of it. They come in various sizes. The capacitor in many circuits uses these little tiny little guys. However, some capacitors are much larger and can be the size of your fist. A capacitor usually consists of two parallel plates separated by a gap through which no current flows. Although no current crosses the gap, the alternating current surges back and forth from plate to plate through the rest of your circuit, as we have shown previously. If we want to model this voltage drop across your capacitor, it's again proportional to the charge on your capacitor, where 1 over C, that's your proportionality constant. Okay. With these three descriptions of our voltage loss, Kirchhoff's voltage law tells us that the sum of these voltage drops has to equal to the input charge that is supplied. So you have your voltage drop across your resistor, which was proportional to your current. Your voltage drop across your inductor, which is proportional to the rate of change of your current. And there's the voltage drop across your capacitor, which is 1 over C times the charge on your capacitor. And this has to equal to the input voltage that's supplied by your power source. Now this DE as it's written has mixed variables. It has both current, I, and charge on your capacitor on the same equation. And when when solving these differential equations, we want to write them as a single variable. Write them with a single variable. And we can do that with some substitutions. So earlier we said that current is the rate of change of the charge. And if that's true, we can take the derivative of both sides of this equation. On the left, we'll get I prime of t. On the right, since there's already a first derivative, we'll get a second derivative. With these substitutions, a DE modeling the charge on the capacitor can be written as follows. So instead of writing the Ri, it's RQ prime. Instead of writing Li prime, it's LQ double prime. Remember, because I prime is Q double prime. And then the 1 over Q, this stays the same. If we change the order of the terms and write it in the form of a linear second order DE, then I write it as LQ double prime, RQ prime, 1 over CQ equals your voltage source. If we're given an initial value problem, we would need to know the initial charge on the capacitor, so Q naught, how much charge is on the capacitor, and we would need to know the initial amount of current flowing through the circuit. Okay. Now you'll also notice that this differential equation, while I am using different letters, it does match the general differential equation we presented in chapter 4.2. And so it is still of the form AY double prime plus BY prime plus CY equals V of t. So the left-hand side still matches the same left-hand side of the differential equation we've been studying all of chapter 4.2. So our solution should still be the same. We just have a new application of this second-order linear differential equation. Let's look at an example. Consider an RLC circuit with a 30 ohm resistor, a 1 Henry inductor, and a 1/200 farad capacitor. We charge the capacitor to 10 coulombs, and then the voltage source is removed. This is what makes the DE homogeneous. And it says there is no current initially flowing through the system. Okay, so let's model this circuit. And I'm going to start by writing the IVP. So looking back, we want to remember that our differential equation is always going to be your inductor, your resistor, your capacitor. So we had a 1 Henry inductor, so just 1 Q double dot, a 30 ohm resistor, so plus 30 Q dot, and a 1/200th farad capacitor. So 1/200th. So remember, it's always 1 over your capacitor. So 1 over the 1/200th. Q. Because the voltage source is removed, that makes the right-hand side 0, and so it's homogeneous. We're told that the initial charge on the capacitor, so Q of 0, is equal to 10 coulombs. And we're told that there is no current flowing through the system, which tells us Q prime, Q dot of 0 is equal to 0. This is our initial value problem. However, I'd like to rewrite this a little bit to make it look simpler. We don't need the 1 in the front, so I'm just going to write this as Q double dot plus 30 Q dot, and 1 divided by 1/200 ends up just being 200 Q equals 0. This is our second order linear homogeneous differential equation. And again, other than different variable, we're using Q rather than X, and we're having different representation of our coefficients. This matches the model, the form of the model we use for spring mass system. So our method for finding the solution is going to be the same. Let's first write our characteristic equation. Again, our characteristic equation is going to be in terms of the variable r, and it'll be a quadratic. And again, these don't have to be factorable, but in our textbook, our author has made all of these factorable. And so we factor it as r plus something times r plus something equals 0, where again you're looking for two values that multiply to 200 and add to 30, which I think is going to be 10 and 20. Multiply to 200, add to 30. And this gives us our two values of r as -10 and -20, which allow us to write our general solution as Q of t is equal to C1e to the -10t plus C2e to the -20t. This is our general solution. Again, if we're trying to solve our IVP, remember that we know initial conditions for the initial charge on the capacitor and for the initial current, the derivative of the charge. And so we need to now also find the derivative of Q of t. So here Q prime of t would be -10 C1e to the -10t minus 20 C2e to the -20t. We know what is happening at time 0 with this circuit. So now let's evaluate Q of 0 and Q dot of 0, which should give us C1 plus C2 negative 10 C1 minus 20 C2. And from our initial conditions, we knew the initial charge was 10 coulombs, and the initial current flowing through the circuit was 0. Again, there's lots of ways to solve this system of equations, but I like using the elimination method. And it doesn't matter which variable you make cancel, but I'd like to make the C2s cancel because I've been doing it that way so far. So let's choose to maybe multiply this first equation by 20. Which gives us 20C1 plus 20C2 equals 200. The second equation stayed the same. And now if we're using the elimination method, we've now set this up so that when we add our equations together, the C2 terms cancel. And we'll get 10C, I want this to be in blue. We'll get 10C1 is 200, or C1 is just 20. Now, it doesn't matter how you find C2, but the way I've been doing this is grabbing my first equation. And if C1 is 20, then we have 20 plus C2 is 10. So C2 had to be negative 10. These are our constants for our initial value problem. This allows us to write the solution to the IVP. As Q of t 20 e to the negative 10t minus 10 e to the negative 20t. Again, you want to observe that this function describes the charge on the capacitor in our circuit. And notice with both of these exponential terms having a negative exponent, we can say that this charge does dissipate over time. Maybe I'll add that. This describes the charge on the capacitor that dissipates as time goes on. And that's because of those negative exponents. Okay, there's one more part to this question, part C, which was find a function describing the current flowing through the circuit. So here you remember that current is the rate of change of your charge. So for part C, you need to recall that your current is I of t, which is Q prime of t. So if you want to describe your current, you find the derivative of your charge function. So here I of t Take your derivative of 20e to the negative 10t is going to be negative 200 e to the negative 10t plus 200 e to the negative 20t. And this would be an equation describing the current flowing through your circuit. And again, you'll notice that because of those negative exponents, this current will dissipate as time goes on. Okay, I hope this is helpful. I wasn't going to do any more examples than just this one because the method that we apply to solving this differential equation matches the method of the spring mass systems. The new piece of information that you'll be working through with this section is how to write your differential equation. But I hope this is helpful, and I'll see you next time.